Hello everyone, I welcome you to another video lesson on testing of hypothesis. In this lesson, we'll look at how to determine whether two attributes are associated with each other or whether two attributes are independent using a simple technique in hypothesis testing. Problems of this type are usually presented in the form of a contingency table where the frequency of observations belonging to each attribute is listed in the form of a contingency table. Now, unlike the Z test or the F test, this set of problems will always involve observed frequencies. So there won't be any mention of the word average or standard deviation or proportion or mean or whatsoever. The observations are in terms of frequencies known as the observed frequencies. They'll be presented in the form of a table having a minimum of 4 columns and a maximum of whatever number of columns that are possible. So a sample of such a table is given here. We compare two attributes and there are four entries O1, O2, O3 and O4. O1 is when both attributes are observed. O2 and O3 are when only one of the two attributes are observed. O4 when both attributes are not observed. We denote R1, R2, C1, C2 as the totals of the two rows and the two columns respectively, and G is known as the sum of all observations in the given table. So that to test whether these two attributes are independent or whether they are associated, we use the statistic known as the chi-squared. So it's called as the chi-squared test. Like the Z test and the F test, we have the chi-squared test. This is calculated using the simple formula OI minus EI whole squared by EI, and we add this ratio across the total number of observations that we have, where OI represents the set of observed frequencies and EI represents the set of expected frequencies. Now, this chi-square test is used for a different purpose also. It is used to test the goodness of fit as well as to test if two attributes are independent. We look at both of them in subsequent videos. The null hypothesis to test whether the independence of attributes is observed is defined such that as it is presented in the screen. The two attributes are independent and that will frame the null hypothesis H0. And the statement that two attributes are not independent will define what is called as the null, which will define what is called as the alternate hypothesis HA. The expected frequencies are to be calculated based on the given data, and they are calculated using the formula as it is available in the screen. An estimate of EI, known as the estimated frequencies, expected frequencies, is an estimate of the expected frequencies is determined by considering the totals of the rows and the columns of the corresponding observed frequencies. So EI is calculated by multiplying the row total and the column total and dividing this product by the grand total of all the observations in the table. Now, once we know what EI is, we can calculate the value of the test statistic chi-squared using the formula that we have already introduced. Now, we compare this calculated value with a table value that depends on two things. One, the level of significance, and two, the degrees of freedom. Since there are two attributes involved, the degrees of freedom are calculated by the product of R minus 1 and C minus 1, where R and C are the number of rows and columns in the contingency table. Based on the level of significance, there are the tabulated values available, and that is shown on the right corner of the screen. As usual, we compare the calculated value, the tabulated value, and we accept H naught if chi-squared calculated is less than the critical value, and we reject H naught if chi-squared calculated is greater than the critical value. And we correspondingly interpret the conclusion based on the problem statement. To understand this better, we look at a simple problem where a survey is conducted across 200 youngsters to determine if the attributes of the nature of employment and the place of residence are associated. So there are two attributes here. The person is either self-employed or not self-employed. The person belongs to an urban region or a rural region. We consider a 1% level of significance to check if these two attributes are independent. So first up, we frame these statements for the null and alternate hypothesis. We see that H naught is as follows. The two attributes are independent. And HA is that the two attributes are not. So we calculate the expected frequencies based on the observed frequencies using the formula we have already discussed. We need the row totals and the column totals for the table given. We found the row totals to be 120 and 80, the column totals to be 110 and 90. So the corresponding expected frequency for each of the given observed frequencies 45, 75, 65, and 15 are calculated as follows. 45 has a row total of 120 and the column total of 110. That gives us an expected frequency of 66. Similarly, 75 has a row total of 120 and a column total of 90. That gives us an expected frequency of 54. 65 has a row total of 80 and the column total of 110. That gives us an expected frequency of 44. And finally, 15 has a row total of 80 and a column total of 90. That gives us an expected frequency of 36. Now that all four expected frequencies are available, we pair them up with the corresponding observed frequencies. We find the differences. We square the differences. All the differences are the same, but that's only a coincidence. It doesn't happen always. We square the differences. We find the ratio with the expected frequencies. That sum comes down to 37.11. So the calculated value for the statistic chi-squared comes down to 37.11. We calculate the degrees of freedom based on the number of rows and columns of the contingency table. There are two rows and two columns, and hence the number of degrees of freedom will be the product of 2 minus 1 and 2 minus 1, which is 1 again. Hence, we have only 1 degree of freedom, and since the recommended level of significance is 1%, we refer to the chart with the chi-square test statistic, and we find that the critical value, the table value for chi-square at 1% level of significance and 1 degree of freedom is 6.635. So the calculated value of 37 is compared with the tabulated value of 6.635, and we see that the calculated value falls in the rejection region, and therefore H naught is rejected. Therefore, we conclude that there is no sufficient evidence to support the claim that they are independent, and therefore there is in fact an association between the two attributes discussed at the start of the problem. We find out that the place of residence and the nature of employment are in fact associated. However, there is a small correction that has to be done in a very particular case while calculating the value of chi-square. Whenever we are comparing two attributes and we see that the degrees of freedom is 1, as in only two rows and two columns are involved, and also when one of the observations is a frequency that is less than 5, we make a small correction known as the eighth correction to make our estimate a little more accurate. This correction is done by subtracting zero point 0.5 from the difference OI minus VI. Once this correction is done, we follow the usual procedure. We square the differences, divide by the expected frequencies, and add up all the ratios. We'll look at one example under this condition. Two batches of 12 patients were considered for an examination. One batch was given an extra medicine A, and the other batch was not. We examine at 5% level of significance if there is enough evidence to state that medicine A is effective against the particular disease. So we have the table here. 3 people who were given the medicine were cured. 9 people who were given the medicine were not cured. 7 people who were not given the medicine were cured. And 5 people who were not given the medicine were not cured. So once again, we are testing two attributes here, the attribute of getting cured and the attribute of uh, medicine A being given. To do this, we'll frame the null and alternate hypothesis, which state that the attributes are independent and the attributes are not independent. We observe that there are four observed frequencies. We note them down here, 3, 9, 7, and 5. And we see that one of them is less than 5, which means we'll have to apply the correction here. So we also do the row totaling and the column totaling. The row totals come down to 12 and 12. The column totals come down to 10 and 14. The grand total comes down to 24. Next, we calculated the expected frequencies using the formula row total multiplied by the column total divided by the grand total that comes down to 5, 7, 5, and 7. So we have EIs at 5, 7, 5, and 7. So we have a set of frequencies here, OI and EI. We find out the absolute value of the difference, and then we subtract zero point 0.5 to make the eighth correction, and we see that the value of the test statistic comes down to 1.5428. We compare this with the critical value, which depends on the degrees of freedom. They have two rows and two columns in the problem. Therefore, we have only one degree of freedom, and the recommended level of significance is at 5%, and therefore the tabulated value from the chart is at 3.841. So we make the comparison here of the calculated value of test statistic, which is at 1.54, against the tabulated value, which is at 3.84. We observe that the calculated value is less than the tabulated value. The test statistic therefore falls in the acceptance region, and therefore H naught is accepted. And this helps us conclude that there is enough evidence to support that two attributes are in fact independent. Therefore, medicine A is not effective against the curing of the disease. This helps us discuss how the attributes are independent based on chi-square test. I'll follow this video shortly with another video lesson where we use the chi-square test to check the goodness of fit according to the recommended distribution of frequencies. Thank you.